Đi sao thiên á? Hi, and good evening, everyone. I'll just start in just a while. So let me just share my screen and we can start. Uh, can you please confirm if my screen is visible and is my audio audible?
Yes, sir. Screen is visual and the voice is clear.
Okay, great. We'll just start then. So in the last class, we saw this particular problem. That is, we left off at this particular problem, right? That is, determine the y parameter of a two-port network whose z parameters are as given, right? So for this, we saw that since your admittance matrix and your impedance matrix are kind of complementary to each other, so Z inverse is equal to Y and Y inverse is equal to Z. So basically, if you take the inverse of the given Z matrix, you can get what is the Y parameter. All right. So that was the question, right? So we will continue doing questions on the two-port networks, right? And then we will go ahead. Okay. Okay, so the next question is find the transmission parameters for the circuit in this figure, that is 6, 1, 12, 2, and 4. Okay, so we have to find the ABCD parameters. Okay, so how do we find this? So what we can do is we can split the entire network into a number of matrices. Okay.
Hello, sir. Hello, sir. Screen is not visual.
Yeah, I am sharing it once again. I realized it. Just a second. Share. Okay, I think now it is fine, right?
Yes, sir.
Okay, great. Okay, so the question is Find the transmission parameters for the circuit shown in figure. Okay, so how do we approach this problem? What we can do is we can split the entire network into a number of matrices. Okay, so for instance, this particular resistor can be represented as something like 1, 6, 0, 1, right? And you know this particular resistor in shunt path can be represented as 1, 0, 1, 1. Okay, and likewise for series elements you have 1, then whatever is the element, and 0 and 1, and for the shunt path you have something like 1, 0, then 1 by 2, and then 1. Okay, because this is the admittance, therefore you put 1 by 2. Okay, and similarly again for the series path, so what you end up is 1, 4, 0, 1. So uh, this is how what you do is like you basically split the entire network into a number of matrices. All right, so once you have the matrices, you can go ahead. Now that these are all in kind of a cascade, right? So the final answer would be a multiplication of all of these matrices. Okay, so this would be this, and you multiply with this matrix, right? And once you get the resultant of this, you multiply with this particular matrix. Then you get the resultant including this, you multiply with the next element and so on. So it's a cascade. All right. So yes, that's how you do it. And yeah. So I think for this particular problem, like I will not be doing the calculations. We can just directly, I think I have just shown you, you can directly multiply the matrices and get the answer. The answer you should be expecting to get is option number C. All right.
Okay, sir.
Okay. So let's go ahead then. Okay. So again, a very similar problem. What you will do is same thing. You write the matrices for each of these. That is 1, 1, 10, 0, 1, and this would be something like 1, 0, 1 by 20, and then 1. Okay. And likewise for the series elements and shunt elements, since they are all in cascade, you can directly go ahead and then you can multiply them. All right. Okay. Okay. So if time permits, we will come back to the ABCD questions later on. But right now, we will go ahead with problems on BJTs. Okay, so that is what is assigned for this particular week. So we will go ahead with that. All right. So the first question is, let me take a new slide over here. Okay. Okay. So the first question is, the transistor is in active mode. The transistor is in active mode in the following circuit. And Vc equals 2 volts. To get Vc equal to 6 volts, we replace Rc by Rc1. Then the ratio of Rc by Rc1, or Rc1 over Rc, is dash. Okay, and they have also given a circuit over here. right? So the circuit is you have 10-volt supply and you have the collector resistor RC, okay, and you have a BJT, right? So okay, and you have VC over here, okay. You are also having a resistor over here, and I call this as RA, right? Or RP, okay. So the point is with this particular configuration, right? With this particular configuration, they are telling VC is equal to 6 volts. VC is equal to 6 volts. Now I want VC equal to, um, initially VC is equal to 2 volts. I want VC is equal to 6 volt. So what should be the ratio of RC 1 by RC is the question. All right. Okay. So simply by looking at the circuit, right? So all questions on BJTs are mostly based on KCL and KVL. Okay, if you know KCL, KVL, you can easily go ahead and solve the problem, right? So over here, just write down what is VC. VC would be basically 10 volts minus ICRC, correct? If this is your IC current, all right? So VC is equal to 10 minus ICRC. And they have told that case 1, right? Case 1 is what? Case 1 is VC is equal to 2 volts. So 2 is equal to 10 minus ICRC, which means that your ICRC is basically 8, right? This is case 1. And in case 2, they have told you want VC is equal to 10 volt, VC is equal to 6 volt, which means 10 minus, now RC becomes RC1, right? So what should happen? So from here we have to get what is RC1 by RC, right? So from this particular expression, I can very well write IC is equal to 8 by RC. Okay. So again, right over here, 6 minus 6 is equal to 10 minus IC is equal to 8 by RC into RC1. All right. So what is the answer? You get RC1 over RC is going to be 0.5, right? Yeah, 8 into 0.5 is 4, so 10 minus 6 is okay. 10 minus 4 is 6. So RC1 by RC is 0.5. Is this fine? Just using KVL itself, we have written the answer. Okay. Just by looking at the circuit, you can write. Okay, it's a very simple problem.
Please
All right.
explain it again.
Sorry?
Please explain it again in one time.
Yeah. So you can understand the question was only this, right? Okay, they have given just the circuit alone. Okay, they have given just this circuit alone. So see what is the collector voltage? Collector voltage is the voltage across this, right? VCE, right? So if you write KVL, what will happen? You start from over here. You start from here. You start from here and come down till this point, right? We have just written what is the potential difference. So 10 minus ICRC minus VC is equal to 0, or 10 minus ICRC is equal to VC, right? So VC is what? VC is basically 10 minus some drop, right? The drop is across resistor RC. So VC is equal to 10 minus ICRC. All right. So they have told that initially VC is equal to 2 volts. Okay. They have written VC is equal to 2 volts, and you have collector resistor RC with RC. Now I am getting VC is equal to 6 volts with another resistance RC1. Okay. if I change this resistor, right? If I change the resistor, my VC will also change because VC is basically based on the drop across the resistor. So if I change the resistor, my VC is also changing to 6 volts. They have given VC was 2 volts, now it became 6 volt. What is the ratio of RC to RC1 or RC1 by RC, right? So that is the question. So basically you wrote the KVL equation and you substitute the values, right? So VC is 2 volts, VC is 6 volts, you get two cases. So IC is basically what? IC is 8 by RC. And from first equation, you substitute it over here, you get what is RC1 by RC. Okay.
Yes, sir, clear now.
Great. So we'll go ahead with the next question. So the next question is the transistor circuit shown uses a transistor with VB is equal to 0.7 volt. The transistor circuit uses a transistor with the base emitter voltage or the cut-in voltage as we call it. They have given that it is 0.7 volts. Okay. And they have also given that IC is equal to IE. And IC is almost equal to IE, approximately equal to IE. Okay. And a DC current gain of 100. Okay. So the question is the value of V naught is dash. Okay. Okay. So the circuit is something like this. So you are having 10 volts over here. All right. And you are having a resistor. Okay. And they are telling this is my V naught. Okay. So we have to take the voltage, emitter voltage. All right. And they have also given this is 150 ohms. This is 100 kilo ohm. And this is 5 kilo ohm. Okay. So the circuit is given, they have given what is VBE, right? And they have told IC is almost equal to IE, DC gain is 100. So what is the value of V naught? Okay. Okay. So first of all, let's write the equation for V naught. So what is V naught, right? So from this itself, you can understand if let's say my emitter current is flowing like this, right? My emitter current flows like this. I'm calling this as IE, emitter current IE. Okay. You know, this is IB and this is IC. Okay. IC and IB are entering and IE is leaving. That is the convention we usually follow. All right. So you know that from this figure, V naught is equal to IE or in this case, IE into 150 ohms because RE is 150 ohms. All right. So IE into 150. Okay. This is your V naught. All right. So we just need to find out what is IE. Okay. You just need to find out what is IE. Okay, and they have also given IC is equal to IE. So if you can find out IC, that is great. Okay, you get the answer, right? Okay, so the first thing we will do is let's go to the next page and let me redraw the circuit once again. So you're having 10 volts over here and you have a resistor, you have another resistor. So your RB and RC are done. All right, and you have another resistor over here, you have the ground and you are taking V naught over here. So this is your 5 kilo ohm, right? And this is 100K and it's only 150 ohms. Okay, now they have told that your cut-in voltage is basically what? Cut-in voltage is VBE. It is 0.7 volts. They have also given this in the problem. Okay, so by that logic, okay, so this is one information that we know. So your VBE is 0.7 volts. Okay, also for a transistor, right, for a BJT, you would know that IC is equal to beta times IB, correct? Where beta is your current gain. Beta is your current gain and it is, so you know IC is equal to beta times IB, right? So this is something you also know. Hmm. Okay. So from the base equation, right? From the base side equation, let's construct the KVL equation. Okay. I will take KVL through the path in yellow as that I have shown. Okay. So apply KVL in the base side. Okay. Applying KVL in base side, right? So what you end up is basically 10 minus 5K into IB, right? Minus VBE minus V naught is equal to 0. Agreed? This is just KVL, right? So 10 minus 5K into IB minus VB is 0.7 volts minus V naught is what? V naught is basically 150 into IE, right? 150 into IE is equal to 0. Okay. So 10 minus 5K into IB minus 0.7 minus 150 into, they have given that IC and IE are almost same in the question, right? IC is almost equal to IE. Okay. So IE can be written as IC is equal to 0. Okay. So 10 minus 5K into IB minus 0.7 minus 150 into IC is basically beta times IB. Okay. So beta times IB is equal to 0. Okay. So which means 10 minus 0.7 can now be 9.3 minus 5K into IB minus beta is 100. Okay. Beta is 100. So it is going to be how much? 150, 0, 0, right? IB equal to 0. Okay. So let's solve for IB. So what is IB? What is IB? Let me take my calculator as well. So you would be getting IB as around 465 microamperes. Yeah. So you get IB is 465 microamperes, which means that your IC, which is beta times IB, is equal to 100 into 465 microamperes. Okay. Which is nothing but 46.5 milliamperes. All right. So this is your IC, and they have told IC is almost equal to IE. Okay. So what is your V naught now? Output voltage. V naught is basically what? IERE, right? We saw this is the drop. V naught is the drop across the resistor IERE, right? So IERE, that is 150 into IE, that is 150 into 46.5 milli. All right. Which you will be getting as 6.975 volts. Okay. So what did we do to solve the problem? It's very simple. Only three steps that we followed. One is IC is equal to beta IB. We know IC is equal to beta IB. They have given that IE is almost equal to IC in the question. Okay. This is something we followed. Second, what? Second was write the KVL for base side, base emitter side. Okay. Write the KVL for the base emitter side. So that is what we did as shown in the yellow line over here. You will get what is IB. Okay. Find IB, and from that you can get what is IC. Finally, find V naught is equal to IERE. Okay. Is this question clear?
Yes, sir, clear.
Okay, great. So let's go to the next problem then. So the next question is that the common emitter amplifier is biased using a 1 milliampere ideal current source. The approximate base current value is dash. So they have given a circuit over here. Let's draw the circuit. So they have given VCC equal to 5 volts. All right. So RC is, okay, let me draw the circuit on the side. Okay, so there is a circuit. Okay, so the common emitter amplifier is biased using a 1 milliampere ideal current source. So the approximate base current value is dash. Okay, so they have given beta is equal to 100. Hmm. And the question is base current value should be written in microamperes. Okay, so yeah, what is this? What have they given? They have given that this particular current is 1 milliampere, right? So what is this current? This current is IE. Agreed? Okay. So IE is 1 milliampere. Okay. And we saw in the previous problem also that IC can almost be approximated as IE. Okay. They have given the term approximated. So which means you can do this. IC is almost equal to IE. Okay. And we also know IC is equal to beta times IB. Okay. So beta times IB, which means that IB is equal to IC by beta. Okay. Therefore, IB is equal to IE by beta or approximately equal to IE by beta, which is basically 1 milliampere divided by beta is 100. Okay. So 1 milliampere by 100 would give you 10 microampere. Agree? Answer?
Yes, sir.
Okay, great. So let's go ahead then. Mm, Let me add some new slides. Okay. Okay. So the question is, so this is a very simple question. During the operation of the transistor in cutoff region. Okay. So IB equal to 0, IC not equal to 0, IB equal to 0, IC equal to 0, IB not equal to 0, IC not equal to 0, and finally IB not equal to 0 and IC equal to 0. So what is the answer? So during cutoff region operation, so in cutoff region means like there is no bias at all, right? Your bias is very low. So in that scenario, what is IB? So what is the answer for this question? The answer would be IB is equal to 0, right? And IC equal to 0. But there is a small trick over here that there can be a very small leakage current. Okay, if you see practically, IC may not be exactly 0. Rather, there would be a very small leakage. IC, we call it the leakage current. Okay, this can be a few microamps. Okay, or nanoamperes. Very low current. Okay, fine. Okay, so let's go to the next question. So the question is, the parameter HFE. The parameter HFE is called dash in C arrangement with output shorted. Okay. Is parameter HFE the voltage gain or current gain? So what is the answer? What is HFE? So HFE is basically the current gain, right? HFE is equal to beta. Okay. 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 So let's go to the next question. Okay. So this is a good question based on op amps. All right. So the question is, the input bias in an op amp when the offset current is 11 nanoamperes. And the base current at the non-inverting terminal is 31.5 nanoampere. So the question is find out the input bias current in an op amp. Okay. So let's break this down. That is, they have told that the offset current is offset current, right? IOS, right? We call it IOS is 11 nanoamperes. Okay. And they have also told the I base current at the non-inverting terminal, IB plus, is basically 31.5 nanoamperes. Okay. IB plus is 31.5 nanoamperes. The offset current is 11 nanoamperes. The question is, what is IB? Okay. What is the input bias current? Okay. Okay. Fine. So what is the offset current in an op amp? You know that the offset current is the difference between IB plus and IB minus. So offset current is basically IB plus minus IB minus. Right? This is your offset current. Offset current is basically the difference between IB plus and IB minus. Okay. And yeah, so this is step number 1, right? That is your IB plus is basically 31.5 nano minus IB minus is equal to I offset. I offset is 11 nanoamperes. Okay. So you get your IB minus is what? IB minus is basically so there is a mod operation that's going on over here. So you'll be getting 42.5 nanoamperes. This is your IB minus. Okay. So now you got your IB plus, you got your IB minus. Therefore, your input bias current is what? Input bias current is IB plus IB minus by 2. That is the average of the bias currents at the two input terminals. Okay. So basically 31.5 nano plus 42.5 nano by 2, which gives you 37.5 nanoamperes. Is this fine? Just you should know what is the bias current and what is the offset current. Okay. The key equations over here are offset current by definition is basically the difference between your two bias currents. Offset current is the difference between two bias currents. Okay, IB plus minus IB minus or vice versa. Okay, and the bias current is the average of the two currents at the input and the output terminals. Okay, of an op amp. So the bias current is IB plus minus IB minus, and the offset current is IB plus minus IB minus. The bias current is the uh, average of the two. Okay. Okay. Is this fine till this point?
Yes, sir. Fine.
Okay, great. So we will go ahead with the next problem. So the next problem is given the following I don't know why. Given the following op amp configuration, how can the output voltage be visualized? When the ideal resistances R1 and R2 are equal. Okay. So they have given you an op amp configuration, right? So this R1, this R2, okay. And they have mentioned that the input voltage over here is a sine wave. Okay. Input voltage is a sine wave. This is your VI. So how would the output look like is the question. All right. So A is just the sine wave again. B is a triangular wave. C is an inverted sine wave. And D is an inverted square wave. So what is the answer? So what is the answer for this question? How would the output look like if I give a sine wave to an op amp? So what is the configuration? So what is the type of this amplifier, right? What is the type of this amplifier? So is this an invert? So where is the input coming? So the input is coming to the inverting terminal, right? The input is coming to the inverting terminal, which means that this is an inverting amplifier. Okay. So you know V naught by Vi is equal to minus R2 by R1, and R2 and R1 are same, which means that it is going to be minus 1. The gain is minus 1, which means that V naught is minus Vi, or there is a phase shift of 180 degree, right? 180 degree phase shift. So the answer would be an inverted sine wave. Okay. So is the question clear? Is the answer clear? How we are getting this?
Yes, sir, clear.
Right. So you did you understand this inverting amplifier part? This particular V naught by Vi
Yes,
is minus R2 by R1. How did it come about? Those are
yes,
clear?
sir. Yes, sir,
Okay.
clear.
Oh, great. Okay. So so the next question is also an interesting question, right? Hmm. So they have given you hmm. So what will be the output? What will be the output voltage? In volts of the op amp supplied with input voltages of 300 microvolts and 284 microvolts, having a differential gain of 10,000 and CMRR 10 power 3. All right. So let's just note down a little what they have given over here, right? So they have given differential gain, right? AD, we call the differential gain as AD. AD is basically 10,000. Okay. And they have told the common mode rejection ratio is 10 power 3, right? So what is 10 power 3? 10 power 3 is again 10,000. All right. Or sorry, again 1000. Okay. So CMRR is 1000. So what is CMRR? By definition, your CMRR is basically what? CMRR is differential mode gain by common mode gain, right? So differential mode gain by common mode gain. So higher your CMRR, more will be the differential mode gain and less will be the common mode gain. Okay. That's desirable always. So CMRR is 10 power 3. Okay. So they have given your AD, they have given CMRR, and they have also given V1 and V2, the input voltages, right? So V1 is 300 microvolts and V2 is 284 microvolts. Okay. So this is your input voltage. From this, the question is find V. Find output voltage V0. Okay. So you know that in an op amp, in any op amp, the output voltage is given by AD, VD plus ACM, VCM. Agreed? Is this fine?
Yes, sir, fine.
So what is VD? VD is basically V1 minus V2, right? Difference between the inputs. And what is VCM? VCM is basically V1 plus V2 by 2. All right. So ideally you would want V0 is equal to AdVd and your ACM should be 0 ideally, right? But that doesn't happen in practice. Anyway, so Vd is basically V1 minus V2, right? Which means 300 microvolts minus 284 micro, which gives you 16 microvolts. Okay. And your VCM is equal to V1 plus V2 over 2. Okay. So 300 micro plus 284 micro over 2. So which gives you 292 microvolts. Okay. And they have given AD is equal to 10,000. Okay. And what is ACM then? ACM is basically from CMRR, right? From CMRR, we can write ACM is equal to AD by CMRR, right? From this particular equation. Okay. So ACM is equal to AD by CMRR, which means AD is 10,000 divided by CMRR was 10 power 3, which gives you 10. Okay. So every detail is available over here. So we can go ahead and find out what is V0. V0 is equal to 10,000 into 16 micro, right? Plus ACM is 10 into 292 micro. So you will be getting how much? 10,000 16 micro is basically 0.16 and this is 0. So V0 is basically 0.16292 volts or 0.163 volts. Is this fine?
Yes, sir, fine.
Great. Okay, so let's go ahead with the next question then. This is your 10th question for the day. So the next question, yeah. The op-amp shown in the following figure has a slew rate of 1 volt per microsecond. The unity gain frequency is 1 megahertz. Okay, so slew rate is given, the unity gain frequency is given. Okay. And the output saturation levels are plus minus 14 volts. Okay. The question is, what is the maximum output frequency? At which undistorted output can be obtained. Okay. They have also given the circuit over here. So they have given the slew rate is 1 volt per microsecond. Okay. And unity gain frequency, F UGF, right, is 1 megahertz. Okay. So what is the maximum output frequency at which you can get undistorted output? All right. So they have also given that the saturation level is plus minus 14 volt. Okay. So let me take some new slides. Okay, so even if you don't know, right, like even if you don't know how to solve the problems, right, we can easily think a little and get the answer. Okay, so what have they given us a slew rate? Slew rate is basically 1 volt per microsecond. Okay, okay, so slew rate is 1 volt per microsecond. I can write this as 1 volt, or I can, hmm, so I can write this as 1 volt. And what is 1 by second? 1 by second is basically hertz, right? So 1 volt hertz divided by and your micro. Okay, just dimensionally, I'm just trying to manipulate a little. Hmm. Okay, so usually we represent not directly in hertz, rather we try to represent it in radians. Okay, so I can write this as radians. Okay, in radians. Okay, so this can be written as 1 volt, okay, divided by micro into radian is basically 2 pi if you want to convert it into hertz, okay, into 2 pi, right? So, what you are getting is slew rate is equal to 2 pi, right? 2 pi into voltage is there. So 2 pi into voltage, 2 pi into volts into, and this is radiances. So this means this is your frequency, right, in hertz. So into frequency. Okay. This is where you would have seen the formula that F is equal to what? F is equal to slew rate divided by 2 pi into V. V saturation, right? So, if you write, so F is basically what? 1 volt per microsecond. 1 volt per microsecond, which means if I write it in proper units, if I convert the micro, I am going to get 1 into 10 power 6, right? 1 into 10 power 6 divided by 2 pi into Vsat is 14 volts. Okay. So what do you get now? 15, 10 power 6 answer. Right. So you will be getting around 11.37 volts. Okay. Yeah. So the catch is this. The frequency is basically slew rate divided by 2 pi into Vsat. So this is the maximum frequency you can go to. Okay, beyond this, the op amp will not be able to measure the frequency. Okay, based on the slew rate and yeah, so based on the slew rate and the saturation level, you can find out what is the maximum frequency. Okay, just these two are enough. Slew rate and the saturation level, you get what is the maximum frequency. Frequency is basically slew rate divided by 2 pi into Vsat. Okay. Okay, so we'll go to the next problem. So find the output voltage for the following circuit. the circuit parameters are given as follows. Okay. Yeah, and they have also given the circuit over here. Hmm. It's a two-stage op-amp based circuit, right? So you have VI2, then R1, you have the R2 over here, and you have R3, R5, and this is VI1. And this is your V0. Okay. Seems to be a very complicated circuit, but no, this is not complicated at all. So let's break it down. All right. Let's break it down. So what is the first part? What is this particular amplifier? What is this particular op-amp circuit? So this you can understand is basically a simple inverting amplifier. Okay. Simple inverting amplifier. And let's say I get the output of this stage as some Vx. Okay. The output of this stage is Vx. Okay. So Vx is coming over here and you see that there are two inputs to this op amp. Okay. So Vx is one input to the op amp and Vi1 is another input to this op amp, to op amp number 2. Okay. Which means this is going to be some kind of summing amplifier. Okay. Or adder circuit. We call it adder or subtractor circuit based on what operation it's going to do. It can be either an adder circuit or a subtractor circuit. Okay, we have to simplify this, but till this point, are you understanding?
Yes, sir.
Okay, great. So let's solve this. We have to. Okay, so there is one more slide. So let me draw the circuit once again. So you are having so this is R1, R2, this is R3, and let me R4. This is your V0. And this is your R5. This is your R4. This is your Vi2. And we told that this can be denoted as Vx. Okay. So what is Vx, right? So what is Vx? The first part is basically an inverting amplifier. So in an inverting amplifier, you know the output voltage is going to be minus Vi1 into R2 by R1, right? It's going to be minus Vi1 into R2 by R1. Okay. Which means in our case, Vi1 is 1 volt and R2 is 5 ohm, R1 is also 5 ohm. Okay. So minus 1 into R2 is 5, R1 is also 5, which means you get minus 1 volt. So you get Vx is equal to minus 1 volt. All right. So Vx is basically minus 1 volt. And you got what is Vx. Now you see that there are two inputs to the next op amp. Okay. So there are two inputs to the next op amp, and for op amp 2, both Vx and Vi2 are inputs. Okay, so based on the theorems that you have studied earlier on, can you tell like what is the theorem that we should use over here? Right, that is, I have two inputs. I don't want to have both inputs at the same time. I will disable one input and see the result of the other input. That will be number one. And number two will be I will disable the other input and see if with this input. Okay. So I will first see the effect of Vx alone, disabling Vi2. And next I will see the effect of Vi2 alone, disabling Vx or making Vx equal to 0. Right. And then I can sum it up. So what is the theorem called?
That superposition theorem?
Correct. So we can use superposition theorem. Good. We can use superposition theorem. Okay. So see the effect of Vx alone. Okay. Vx alone will be 1 and Vi2 alone can be the other case. And if you sum both of these up, if you sum the response of both of these up, you can get what is V0. Okay. Fine. So then if I have to make Vx alone, then it automatically means that Vi2 equal to 0. And if I have to say what is Vi2 alone, if automatically it means I should keep Vx equal to 0. That is a given. Okay. Okay. So let's simplify the circuit. I will draw the short circuit alone. Right. Just we are having Vx over here, which is minus 1 volts. We already decided, we already computed. So there's your R3, R5, R4. This is Vi2. All right. Okay. So, well, let's split it into two cases then. So, if it's only Vx alone, Vi2 equal to 0, right? So there is no effect of R4 at all, correct? Okay. So if it is only Vx alone, then again this is a simple inverting amplifier. Okay. Therefore, your V0 is going to be
or V naught X, let me call it, it's going to be what? Minus Vx into R5 by R3, right? So Vx is minus 1 into R5 by R3, right? So what is R5, R3? R5 is 10, R3 is 2.5. Okay, which gives you 4 volts. And if you want to see Vi2 alone, which means Vx equal to 0, therefore your V naught 2, right, would be minus Vi2 into R5 by R4. Why R4? Because you see from the path of Vi2 it is R4, right? From the path of Vx it is R3, right? So minus, and Vi2 is given as 5 volts, minus 5 into again 10 by 0.5, which would give you minus 5 into 4, which is minus 20 volts. Okay. So by superposition, V naught is equal to V naught X plus VO2, that is 4 minus 20 minus 16 volt. Is this fine?
Yes, sir, fine.
Okay, just we apply superposition, right? Okay, so before we go ahead, let's look at a recap of what all we have done today. So this question was on op amps. We had 2 cascaded op amps. Just simplify the circuit, use superposition if required. Okay, just use superposition and you get the answer. Okay, disable the other. You identify the kind of op amp circuit that you are having. Okay, that is one. And before that, what is the maximum frequency given the slew rate and the output saturation level? You know that the frequency is going to be slew rate by 2 pi into V saturation. That's the maximum frequency that the op amp can respond to based on the slew rate. For that, we made use of this particular formula, slew rate by 2 pi into V. And before that, we were having a question on CMRR, AD, V1, V2. So we know V0 is equal to ADVD plus ACM, VCM. We would ideally this should be made, V0 should be ADVD alone, ideally, but practically speaking, you have a very finite CMRR. It's not infinite, which means there will be some ACM, right? Some common mode gain that gets reflected. That should be very small. Okay. So VD is V1 minus V2 and VCM is V1 plus V2 by 2. That's the common mode input, average of the two inputs, and VD is the differential input. Okay. And CMRR is basically what? CMRR is AD by ACM. Okay. So another interesting question was on the offset current and the bias current. So offset current is a difference, that is IB plus minus IB minus, right? Difference. So offset current is basically the difference, whereas bias current is basically the average between IB plus and IB minus. Okay, you just need to know this and you can solve the question. So bias current is IB plus plus IB minus by 2 and IOS is IB plus minus IB minus. Okay. Okay. So parameter HFE is nothing but the current gain, and we saw a few problems which can be directly solved by having knowledge of IC is equal to beta times IB, just applying KVL equation in the collector side or in the base side, right? That is what we saw earlier as well. We just applied KVL and that was it. All right. Okay. So let's go ahead and do the last question. Okay. So this will be the 12th question for the day. Find the output voltage V naught. For the following circuit. So the circuit parameters are given as follows. So they have given you what is V1, V2, right? And they have given you all the resistor values. Okay. So let me draw the circuit over here. The circuit is a bit tricky, right? But it's very solvable. Okay. Okay, this is a circuit. So find out the output voltage. Okay. Okay. So for these kind of problems where you see that there is kind of a feedback path, there's kind of a feedback path between from here to the output, right? And there is also a feedback path from here to the output. Okay. For these kind of problems, let's have a starting point. All right. So we don't know this particular node. Okay. So let me call this particular node as Vx. So what is this particular node? If this is Vx, what is this node? If this is Vx, what will be this particular node? By concept of virtual short, right? So by concept of virtual short, you know that V minus is equal to V plus in an op amp, right? V minus is equal to V plus in an op amp. That will be your Vx. Is this agreed? Is this fine?
Yes, sir.
Okay. So the point is at the negative terminal, right? So at negative input terminal, you have your Vx minus Vi2 by R1. This is just node analysis. I'm just writing the node equations. Plus Vx minus V0 divided by R2 equal to 0, right? This particular current and this particular current. Okay. Okay. So in the question they have given Vi2 is ground, right? Vi2 is ground means Vi2 is 0. Okay. So Vi2 is 0. Therefore, your Vx divided by R1 is 1.25K. 1.25K plus Vx minus V0 divided by your R2 is 2.5K equal to 0. Therefore, 2Vx plus Vx will give you 3Vx minus V0 equal to 0. This is one equation. Okay, this is one equation. Okay. So yeah, let's take a new slide. And I have to copy and paste over here. So at the positive input terminal, you have Vx, which is again here also you have only Vx, right? So Vx minus Vi1 divided by R3 plus Vx minus or Vx by R5. So we wrote this current, and Vx minus V0 by R4 equal to 0. Okay, just we are writing the currents. Okay, so Vx minus Vi1 is 5 volts divided by your R3 is 2K. Right, and Vx by R5 is 10K and Vx minus V naught by R4 is 5k equal to 0, right? So you have, if I multiply by 5 Vx minus 25 plus Vx plus 2Vx minus 2V naught equal to 0. Which means 8Vx minus 2V naught equals 25. Okay. So now what you have got is two equations by applying KVL at the positive terminal and at the negative input terminal. So you have got one equation over here, 3Vx minus V naught equal to 0, and the other equation over here, 8Vx minus 2V naught equal to 25. Just we apply KCL, right? Just apply KCL at the two input terminals, and we know that this is also Vx means this is also Vx. Okay, by virtual short concept. Okay, so let's take another slide. So you have got one equation, that is 3Vx minus V naught equal to 0. The other equation is 8Vx minus 2V naught equal to 25, right? So this can be written as 6Vx is equal to, I'm sorry. From this equation, you can write V naught equal to 3Vx. So 8Vx minus 6Vx equal to 25. Therefore, your Vx is equal to 12.5 volts, right? So V naught is 3Vx, which is 3 into 12.5, and this gives you basically 37.3. Is this fine?
Yes, sir.
Okay. So basically we just applied some KCL, right? So that is enough. So just we apply KCL at the inverting and the non-inverting input terminals. Okay. Yeah, so I think we have seen all the problems for the day. So we can wrap it up over here. So thanks for attending. Do you have any doubts regarding today's session?
No, sir, no doubt.
Just okay, great. Just use basic equations. Okay, basic things like KCL, KVL, and knowing IC is equal to beta times IB. So those things are enough to get you through the line. Okay, you do superposition theorem, but just that there are a few questions wherein you need to know the specific formula, as we can call it, right? The frequency is basically what? Slew rate by 2 pi into the saturation voltage. So that should give you the frequency. This is one relation. And another relation is V naught is ADVD plus ACM VCM, where VD is V1 minus V2, VCM is the average, V1 plus V2 by 2. And based on CMRR, you have CMRR is equal to AD by ACM. Okay, differential mode gain by common mode gain. Ideally, you want CMRR to be infinity, which means that common mode gain should be 0. So no common mode noise should enter the system. That's the idea behind it. And finally, the input bias current is basically IB plus IB minus by 2. Again, the average. Whereas the offset current is the difference, IB plus minus IB minus. Okay. Okay, so we will wrap it up over here, and thank you for attending. Yeah, we will meet again in the next week. Okay. So yeah, and yeah, happy festivities, happy Holi, everyone. So yeah,
Happy Holi, sir.
have a great
Sir,
Yeah.
sir, kind request, sir, please upload the YouTube video today evening, sir, by today night, because every time we don't get that time to practice the problems before we submit the assignment, sir.
Oh, okay, okay. Fine. I upload. Last time I was held up with some work. Actually, I remembered you told, I think, but
Yes,
last
sir.
time
Yes,
I
sir.
had some immediate work, so I had to leave immediately. Okay, now, okay, I will sit and upload it now.
Last week, actually, there was a heavy rain in Odisha, sir. That's why we could not attend the class. I was just attending in the last 10-15 minutes, sir.
Okay, okay, okay.
Okay,
Fine,
sir.
fine.
Okay, sir.
Okay,
Please,
I will make
please.
sure I upload it today itself.
Okay, okay, sir. Thank you very much, sir.
Okay.
Happy Holi, sir.
Okay, okay. Good luck. Yeah, happy Holi. Bye.